Welcome, curious minds, to another deep dive. Today we're kicking off a very special series. It's tailored specifically for those of you gearing up for the CSWIP 3.1 Welding Inspector Exam. Think of this as your essential prep toolkit. We're not just giving answers. We're really going to unpack the why behind them, to help you become a truly outstanding inspector.
That's exactly right. It's about grasping the core concepts, not just memorizing. Every question we tackle today is designed to build that deeper understanding, practical insights that you can actually use.
Okay, let's jump right in. First challenge. Think about needing ultimate precision, a really clean weld. The question is, which welding process utilizes a non-consumable electrode? Is it A, SOW, submerged arc welding, B, MMA, manual metal arc top, C, TIG, tungsten inert gas welding, or D, MIG, metal inert gas welding? Take a sec.
Think about how those electrodes work. Okay, so the key word here is non-consumable. We need a process where the electrode doesn't, melt into the weld pool. That immediately points away from things like MMA and MIG. Their electrodes are designed to be consumed. The one that really fits this description is C, TIG.
TIG.
Yeah.
Right, and that non-consumable part is, well, it's kind of the genius of it, isn't it, for those critical jobs. But hang on, if the electrode isn't melting, how does the filler metal actually get in there? And why is that separation so important?
Great question. It gets right to the heart of TIG. The electrode is tungsten. Tungsten has this incredibly high melting point, so it carries the arc, delivers the heat, but stays intact. The filler metal, that's added separately, usually by hand, sometimes automated. And that separation gives the welder, immense control over the pool, the heat, how much filler goes in. It means cleaner welds, less spatter, just top-tier quality control, really vital stuff for tricky materials or thin sections.
Oh, okay. So it's like surgical precision compared to other methods. That separate control is key. Mm-hmm. Right, moving on to our next one. This is about sheer energy, power. Think big fabrication jobs, efficiency, deep penetration. Which of the following welding processes would give the highest heat input when using typical parameters? A, TIG welding. B, manual metal arc welding. C, submerged arc welding. Or D, metal active gas welding. Which one brings the most heat to the party?
Well, when you're talking maximum heat input, one process really stands out as a powerhouse. It operates at really high currents, high voltages, sometimes even multiple wires. The answer is C, submerged arc welding.
So, okay, definitely the powerhouse. But that much heat sounds like it could be a bit of a double-edged sword, maybe. For you, as an inspector, what are the hidden risks? Beyond just, welding fast, what should you be looking out for?
That's a really crucial point. High heat input is great for productivity, yes. Deep penetration, high deposition rates. But metallurgically, it can cause problems. You can get larger grains in the weld in the HAZ, the heat-affected zone. Larger grains often mean lower toughness, more risk of brittle fracture. It can also mess with the microstructure in alloy steels, maybe reducing corrosion resistance, or worse, leading to cracking, sometimes delayed cracking. So for an inspector, understanding this means you need to scrutinize that WPS, the welding procedure spec. Look at preheat, interpass temps, maybe PWHT. It's making sure that speed doesn't compromise the weld's integrity down the line. It's a balancing act.
Right, so it fundamentally changes the metal on a tiny scale. Mm-hmm. Speed is good, but not at any cost.
Got it. Okay, question 3. Let's talk protection. Shielding the weld. Which of the following can be used as a shielding gas in TIG welding? A, argon.B, helium.C, nitrogen.D. All the above. Think carefully on this one. Yeah, this one trips people up sometimes. Argon is the default thought for TIG. It's the most common. But TIG is actually more versatile than you might think. The correct answer here is D, all the above.
Nitrogen.
Yeah.
Really?
Yeah.
That's surprising. We should try to keep nitrogen out, right? As a contaminant. So what's the deal? Why would you want nitrogen in the shielding gas for certain stainless steels? What's it actually doing in there?
It does seem counterintuitive, doesn't it? Normally, yes, nitrogen from the air is bad news. But for specific materials like duplex stainless steels, sometimes super duplex, even some copper alloys, nitrogen can be beneficial. When you add a controlled amount to the shielding gas, often mixed with argon, it helps promote the right microstructure. In duplex steels, for instance, it helps form austenite, balancing the ferrite-austenite ratio. That balance is key for their strength and corrosion resistance. So it's not just inert shielding, it's actually playing an active, beneficial role in the metallurgy for those specific grades. Argon's still great for general use and arc stability. Helium gives you a hotter arc for thick stuff, but nitrogen has its place. It shows the nuance involved.
Wow. Okay, so it's not just any gas, it's the right gas for the specific metal and the specific properties you need. That definitely broadens the perspective. Okay, next question. This one's critical for preventing some really nasty defects. Hydrogen cracking. The term low hydrogen electrode is often used for certain electrodes. What type of covering will they have? A. Cellulosic. B. Rutile. C. Basic. D. Acid. Think. Low hydrogen. What's the coating designed not to have?
Right. Low hydrogen is the key phrase. These electrodes are specifically designed to minimize hydrogen pickup during welding, and the coating type most associated with that characteristic is C. Basic.
Basic coating. Got it. Designed to be dry. But you hear about special handling, right? Baking them. So imagine you're inspecting and you find a box of these basic low hydrogen rods just sitting out, maybe looking a bit damp. What's the immediate red flag there? What's the first thing you tell the welder or supervisor?
Oh, that's a serious red flag. A potential nightmare scenario, really. If those basic electrodes absorb moisture from the air, they completely lose their low hydrogen property. When you weld with them, that moisture breaks down, releasing hydrogen straight into the weld pool. The immediate concern: hydrogen-induced cracking, delayed cracking. It might not show up right away, but it can cause catastrophic failure later, especially in high-strength steel. First thing you advise: stop. Those electrodes need to be quarantined immediately, ideally rebaked according to the manufacturer's exact procedure. If there's any doubt about their condition or if they can be properly baked, discard them. The risk is just too high.
Wow. Yeah, it makes you realize following storage procedures isn't just red tape. It's fundamental safety. All right, last question for this session. Let's think practicalities. Out in the field. Portability. Ease of use. Which welding process is best suited for outdoor applications where portability and ease of use are essential? Hey. Submerged arc welding, SOU. Gas tungsten arc welding, GTOC, DME. Shielded metal arc welding, ISMACE to stick. D. Flux cord arc welding, FCW. Picture yourself on a windy construction site, maybe somewhere remote.
Okay, yeah, outdoors portability. You need something robust, simple, and ideally self-sufficient. SAW is too bulky. TIG needs gas shielding, which is tricky in wind, plus delicate torches. The clear winner here, the real workhorse for these conditions, is C, shielded metal arc welding, SE, SCMU, stick welding.
Stick welding makes total sense. Simple, rugged. But I have heard some folks mention FCW flux cord for outdoor work too. Sometimes they say it's faster. As an inspector, how do you weigh that? When might FCOD actually be a better choice than stick, even if it's a bit more complex?
That's a good comparison. Both SCW and some types of FCAW, the self-shielded ones, don't need external gas, which is great outdoors. But SAW equipment is just simply power source, cables, holder. That's basically it. The electrode is the shielding and filler. FCW needs a wire feeder, the spool of wire itself. It's just a bit more kit to manage. Now, where FCAW can win is deposition rate. It can often lay down weld metal faster than stick, especially on thicker material. So if the job involves a lot of welding, speed is critical, and the conditions aren't too difficult for the slightly bulkier setup, FCW might get the nod. But for maximum portability, simplicity, dealing with really windy conditions, or remote repairs, SMAW stick welding is usually the go-to. As an inspector, you check if the chosen process really fits the specific demands of that job and environment. Is it truly the most appropriate?
Right. The right tool for the job, considering everything. I've seen guys trying to TIG weld outside in the wind. It looked challenging, to say the least. You really appreciate stick in those moments. And that brings us to the end of this deep dive. We've hit some key CSWIP 3.1 topics: TIG's precision, SAW's power, the surprising range of TIG gases, why low hydrogen matters so much, and stick welding's field reliability. Remember, it's not just getting the answer right, it's truly understanding the why. That's what makes a great inspector.
Absolutely. And maybe the question to leave you with is this: how does really getting these fundamentals change how you approach an inspection? How does it help you spot potential problems before they happen, ensuring quality and safety? It's about moving from just checking boxes to, truly understanding the process, proactive, not just reactive.
Couldn't have said it better myself. Thanks for joining us on this deep dive, everyone. We'll be back with more essential insights next time.